Welcome back, everyone. Any questions before we get started? Okay, we're in chapter 5, and that means we're studying matched asymptotics and boundary layers. We more or less finished talking about this linear singularly perturbed problem that I'm using to introduce or reintroduce this topic of matched asymptotic analysis. But I do want to go back to the matching point just to make sure everyone is on a is clearly understanding what's going on with that. So for matching, we introduce this intermediate variable W, which is defined as x over eta. At this point, usually we've determined what delta is, and delta is somehow related to eta in a way because x and z are related. And so we get this relationship here. Now, what we want for this eta scale, this intermediate scale, is the following properties. Eta should be positive for all epsilon. It's a function of epsilon. So you can think about like this. A common example is delta will be epsilon and eta will be some fractional power of epsilon. Now, it turns out the scale changes as we change the parameters m and n as the upper limits of our inner and outer solutions, as we'll discuss. But for now, we can think if m and n are fixed, then this is a fixed scale. Eta has to go to 0 as epsilon goes to 0, as this does. And delta has to go to 0 faster than eta. So that when I divide delta by eta, I'm still going to 0 as epsilon goes to 0. And of course, you see that happens here. If I divide delta by eta, I get epsilon to the 1/2 power, which still goes to 0 as epsilon goes to 0. And all of those three conditions are represented by this little shorthand. We never really talked about what this notation means. Some books really do introduce this notation, but from our point of view, this just means that this is a number that doesn't change with eta or with epsilon, but these do. These get very small. And so for our matching, we're going to do the 1-1 matching as we did last time, just to remind you what's going on here. I'm going to take the first two terms in my expansion for the outer solution, y0, y1, and I'm going to write them or rewrite them in terms of the W variable, W and eta. Well, x is equal to W times eta. So what this means is I'm essentially going to, whenever I have this term, expand it in a series, kind of like a power series, where the terms of the power series are going to be constants plus powers of epsilon, powers of eta, and mixed powers of epsilon and eta. And we keep in mind here that delta is usually determined at this point. We do the same thing with the inner solution. The inner solution is naturally written in terms of the inner variable, the stretch variable z. We write the two-term expansion in terms of W, eta, and delta. Again, delta is known at this point. And we create another power series. And the power series is in terms of powers of epsilon, eta, and combinations of epsilon and eta. We're going to collect all the terms which are, so let me see if I can say this correctly. I was saying smaller than, but it's smaller in an exponential sense, which are larger than order of eta. Because every term which is thrown into this wastebasket is a really small term. So actually this is a larger term. So we're going to write all the terms which are larger than little o of epsilon. Same with this, all the terms which are larger than little o of epsilon. This is our little waste can, and it collects all the terms which are little o of epsilon and smaller. We keep in mind that W is finite. In this case, W is also positive. I'm going to show you a case where we have a boundary layer in the middle of the domain, and W can be both positive and negative. But W is crucially not equal to 0. Okay, W is crucially not equal to 0. It's finite and positive in that case. For matching, what we do is we try to find those unknown constants, coefficients in the inner solution so that it matches with the outer solution, and that common function is what we're going to call the 1-1 match. Once we know what the 1-1 match is, that's kind of represented in these two functions, these two expansions. And so to get a composite solution, we can combine the outer solution, the inner solution, but we have to subtract off where they match because otherwise we're going to double count. So we subtract off the matching function, and that gives us an approximation in terms of x and epsilon only. Notice that I've converted from z to x and delta. Delta is known. And I've converted this guy, which is w, to x over eta. And eta is not going to be known, but it actually knocks out the etas in a nice way, as you'll see. Now, the etas can be chosen, but it's not necessary to do so. This replacement is always going to knock out an eta that's already there.
I thought we chose it last.
You can, but you don't have to. I think we said
1/2.
it could be this, but it doesn't have to be fixed at that value. Usually what we determine is that it has to have a power which falls in a certain range. Okay, it could be between 1/2 and 1, but not including 1/2. And it can't go all the way up to 1, right? If delta is equal to epsilon, because if it does that, then this one would not be satisfied. So we say the width is shrinking. The width of the matching layer is shrinking because the exponent on this exponent here starts to approach 1. Okay, so that's how we get this uniformly valid composite solution. We use the outer and the inner, but we subtract off any matching. So all you have to do then for the whole process is find that match. So last time we started with the outer solution, and I'm just going to confess, the reason why I know what to do with the outer solution is actually I did the inner solution first. Okay, and I knew what I needed. Sometimes it's easier to do the outer solution first, sometimes the inner solution first. What is done in reality is that you kind of do them simultaneously and see what you need. Okay, you keep as much as you need and you discard the rest, and you'll find out how to do that. So the outer solution, the outer expansion, keeping the leading order and the first order terms only. So there's no plus order epsilon here, it's just the first two terms. So there it is. First two terms written out is a function of x and epsilon. We replace x with w times eta, and then we start expanding, because once we do that do this introduction where w is equal to, or x is equal to w eta, then we can have transcendental functions. We can have all kinds of interesting functions. But what we really need is a power series in terms of powers of eta and epsilon and combinations. So this guy here is already of that form. It's already essentially a sequence or series in terms of powers of eta and epsilon and combinations. So this one gives us an epsilon here only, and the combination of this is epsilon times eta. This guy out here is a little more complicated. Remember, W is an order 1 parameter, eta is a small parameter. So we're going to do an expansion of this. In fact, we can break this up into e to the 1 times e to the minus w eta. We're only expanding the e to the minus w eta. We're going to expand that up to the second order term in eta, and everything else is going to be little o of eta squared. Why is everything else little o of eta squared? Well, the reason is because this is a Taylor series. This is the beginning of a Taylor series expansion. In fact, I can write it as a Taylor series with a Taylor polynomial plus an exact remainder, right? So why is this term, this is something I wanted to highlight. Why is this term little o of eta squared? Well, actually that term is going to be something like a constant times eta cubed. And to show that it's little o of eta squared, we have to be able to divide by that and show that that goes to 0 as epsilon goes to 0. Now, does this go to 0 as epsilon goes to 0? Yes, no problem, because I'm going to cancel this and I cancel that, right? So I get c times eta, and eta goes to 0 as epsilon goes to 0 by assumption. So that's taken care of. All right, but it gets a little more intricate than that, because I have to keep a bunch of other terms or decide whether or not to keep terms. So I have a polynomial in epsilon and eta here and 1 in epsilon and eta here with some order 1 constants floating around. So multiply those two things together and collect like terms, and you get an expansion which looks like this. I try to write this starting with the largest things first, going to the smallest things. So the largest thing would be an order 1 term. Next would be an order eta term. Now this guy, I don't know if this one is larger than that one. I don't really know. So I'll just keep them in that order. For example, if eta is epsilon to the 1/2 power, then this is exactly the same order as that. Now for now, I'm not going to worry about or make a distinction. I'll just keep it as is. So the next term, so all you're doing in this case is just multiplying 1 times each of these, and then you do the epsilon term times each of these, and then finally this term times each of these. Now, when I collect everything in this waste bin here, I can write all of those collected terms as order eta squared, because they're all going to remain little o eta squared no matter what. If I multiply it times 1, that's still going to be an order eta squared term. If I multiply it times an epsilon, then it only gets smaller, so it's still little o of eta squared. Same with this one. If I multiply it times an eta epsilon term, this order eta squared term is going to stay order eta squared. It's actually going to be smaller than that, but I don't care that it's going to be smaller. So in any case, I write out my little series like this, and it terminates with order eta squared. But now I know by foreknowledge, I guess, or actually looking forward and seeing what I get with the inner expansion, that I'm only going to have 3 terms. And so I've got to get rid of some of these terms. So I start with this. This is just copied from the previous page. And I'm going to keep only terms up to order epsilon. Everything else is going to be order little o of epsilon. However, everything here is clearly going to be little o of epsilon, except this and this I don't really know. I don't quite know. Well, actually, I'm going to assume that this guy is little o of epsilon. Okay, that assumption is right here. If I make that assumption, then this term is going to be collected in this waste bin, as is everything else. This term is as well. So if it's little o of eta squared, then this term is going to be little o of epsilon for short. So that's a little exercise for you to do, okay, on your own. So it's not hard to show, but it is a little calculation. But if I make this assumption, this sets the scale of epsilon, or this sets the epsilon scale for eta. Okay, so that may not be clear, but we discussed this previously. So what is this saying? So can we have, if we write eta as some power, it could be written as epsilon to the alpha. What is this saying? Can we have alpha being equal to 1/2? The answer is no, because if we select 1/2, then this limit is 1, and we don't get this term to be order epsilon. However, we could have this being, so what could we choose for this? Well, we could have eta, sorry, I keep saying eta, I mean alpha, greater than 1/2, but less than 1. Okay, what if I do that? That could be something like 2/3, for example. If I do that, then this would be satisfied. So it's telling me that I can't have a scale which is eta being epsilon to the 1/2, but I could do something like 2/3. However, I still don't have to specify what that scale is exactly. Well, no matter what, I have these 3 terms now. Actually, it's still 3 terms because you can multiply this guy in, and that's what we'll do in a moment. But I get these 3 terms, and by definition, this has to be my 1,1 outer match function. So notice there are no unknown coefficients in this guy. Absolutely no unknown coefficients. Everything is known in the outer solution. So this 1,1 outer solution, or this 1,1 outer match function, is going to be completely nailed down. Now for the inner expansion, I do the same thing. I write the leading order and the first order, and I have this. So there's the leading order term. There's the first order term. We determined these last time by going through the various problems and calculating these things by a recursive algorithm. So I won't do that again, but you can look back at the previous slides to see that. Same idea. I'm going to replace z with the variable w. That includes then carrying along delta, or eta over delta, but now I'm putting in the fact that I know that delta is exactly equal to epsilon. Here I have some stuff to do, which is a little bit complicated, and because of I was speeding through this last time, I didn't have time to really dwell on this too much. But this is going to be a transcendentally small term. Okay, as is any instance of e to the minus 2w eta over epsilon. And the reason is because of this balance eta over epsilon. What do I know about that? Well, I know that eta goes to 0 as epsilon goes to 0. Of course, epsilon goes to 0 as epsilon goes to 0. But what about this term? Eta over epsilon. What does that do as epsilon goes to 0? Epsilon is going to 0 much faster than eta. So this is going to actually blow up, right? So this goes to infinity as epsilon goes to 0. Well, what's the import of that? That means that this is going to be a transcendentally small term. Same with this, same with that. So in every instance of that transcendentally small term, I'm going to write it as little o of epsilon to the r, a to the r, where r is arbitrary. R can be an arbitrarily large positive number. And the reason why I need this is going to become apparent in a little bit. So do that replacement everywhere. That simplifies a lot. Actually, the only really hard problem here is replacing that transcendentally small term with its with this term here. The only thing of substance then is this z term. When I do this replacement of z with the w times eta over epsilon, I get this term here. And that's what I want to keep. Now, it might seem like a bad term at first, but this epsilon that appears here is going to kill this epsilon here. So this will be a simple power term in terms of epsilon and eta, which is what I want. Okay, so let's go to the next page. So just rewriting things here. So now I want to hide these guys in an order epsilon term. So how do I do that? This guy might not go to 0 very fast. Okay, well, I should say epsilon over eta might not go to 0 very fast. Think about it. This could be something like, let's suppose that eta is 2/3 as we've just chosen, right? So this is going to 0 like epsilon to the 1/3 power. What am I going to need to get this to be little o of r? Well, by itself, it's not going to go to 0 fast to be little o of epsilon. However, if I raise it to the r power, I might get there. What power do I have to raise it to get this to be little o of epsilon? With the assumption that eta is 2/3. Well, this is going to be epsilon to the 1/3. So I need r to be bigger than 3. So if I take r to be equal to 4, that does it, right? Because then this, if r is equal to 4, then this is going to be epsilon to the 4/3 power. And that's definitely going to be order epsilon, because if I divide that by epsilon, that goes to 0. Okay, so it's very important when you play around with these transcendentally small terms that you keep in mind, I have to make this or choose this r large enough to make this little o of epsilon, because I'm going to want to put that in my little o of epsilon waste bin. Does that make sense to everyone? Okay. The only term that really kind of survives is that one that was obtained by doing the replacement for z. So that term there just survives with its multiplication with 1. This epsilon kills this guy and produces this term here. So I went over this really fast last time, and I just wanted to make sure everyone understood where these things are coming from. Now, when I did this, I'm only ever going to get these 3 terms to pop out. That's it. So that guided me in my selection back here to get these 3 terms to pop out. If I would have accepted this term here, I wouldn't have been able to do a match. Okay, it would have said that things are inconsistent. But for matching, I have the choice for the size of n and m, what I want to choose for my eta scale. All right, so I chose to make this guy smaller than what I'm going to consider so that it falls away and I only get these 3 terms. Everything else is clearly going to be order little o of epsilon. Any questions about that? So that's kind of a crucial step that you're going to find out about when you do a homework problem in this area as well, okay? How do I balance things when I'm doing my inner and outer expansions so that I get exactly the right number of terms to do my matching? Okay, so this tells me that this is my 1,1 inner match function. And now this guy does have unknown coefficients. In fact, at every term, there's an unknown coefficient that I have to solve for. So I'm going to set that exactly equal to my outer solution, my outer match solution. So I want my inner and outer solutions to match. The only way this is going to happen is for C0 to equal e to the 1. I get a redundant term somewhere, don't I? Here. This guy has to match with that. Well, thank goodness this is exactly the same function. And once I set my C0 to match this guy, it also matches this term as well. Okay, and that's just because you're dealing with the same function. There's going to be some redundancies. I only have one term to set that C0. Luckily, it happens with this guy. Now, what about C1? actually, sorry, I should say there's two terms from which I can choose that C0. Okay. Luckily, it's consistent. Luckily, they're consistent. And what about this guy, this epsilon term? There's only one epsilon to balance it over here. So that's the one I'm going to choose. So I'm going to have to set C1 to be equal to E1 e to the first power over 2. If that happens, then I get a match. And so the two solutions match. And I set my match function to be the common one. In fact, it was just equal to the outer solution match to begin with. And this is going to be the story that's always happening, or that you'll see happening over and over again. It's all the match function is always going to be this guy once you've chosen the scale appropriately and correctly. Now you can't choose this eta arbitrarily because I have to match with the 1, 1. So this guy really is influencing how this is going to turn out. It's just that the coefficients, the unknown coefficients, only appear over here. So this determines my 1, 1 match function. The algorithm is, as usual, to get my composite solution, outer solution plus inner solution minus the matching function so I don't double count. All right, here was my outer solution part. That's the 0th order term and the 1st order term. Then for the inner part, I have this term and this term. Okay, so this is outer, inner, and match. And notice I've put everything in terms of x and epsilon only. Now remember I said when I do this substitution here, this is going to kill an eta, which appears in the match function. So where is that guy? Right here. So once I do the replacement, I'm going to do the replacement right there by replacing w with x over eta. And notice that that nicely kills off this eta term here. So the exact scale of eta never comes into play. That's a very important concept. The exact scale of eta never comes into play. You might have thought, oh, eta is hanging around in this. I'm going to have to set that scale of eta I'm going to have to set the power of epsilon. I'm going to have to choose it to be something. You don't actually have to choose that because once you do the replacement, w is x over eta, this guy gets killed off and you go back to the x variable. So that's why that guy just becomes x. Now, some nice cancellation happens with all of this. For example, you can see that this term here kills that term and a few other terms as well. In fact, these terms here really only kill off terms that appear in the inner solution match, or sorry, the inner solution up to 1st order. So you'll see this guy kills that. What else do I have? This one is going to kill that term there in combination with that and that. And then finally, this term here kills that term when I multiply by epsilon. So there are 3 terms that get killed off in the inner solution expansion, and that simplifies things quite a lot. This is the structure that you're going to see over and over again for the approximate solutions for singularly perturbed problems. You're going to have something which is just in terms of x, and then you're going to have something which is in terms of x over epsilon, and maybe some other things. And usually it's going to be exponential with a power minus something times x over epsilon. So that's a common feature that you're going to see again and again. So this is our composite solution, 1-1 composite solution. It's easy. Now this is actually this part here would be much easier to do. It's easy to go back and find out what the 0-0 composite solution is. That involved a lot less work. And it turns out that's just these two functions. And again, no matter what order you're at, you're always going to have something which is a function of x and something which is a function of x over epsilon. This is what we get from the outer contribution, and this is what we get from the inner contribution. And notice what happens when I subtract off the match function here, I am going to get some cancellation. So usually whatever terms you put in here are going to seek out and destroy a few of the terms that are appearing in the inner solution expansion. All right.
One terminology question. So would you call like a matching zone between delta and eta?
What do I call the matching zone?
You call that thing like a matching zone?
I call it the matching region, usually. Inner region, outer region, matching region. Or inner zone, outer zone, matching zone.
Do you give any justification why we picked NM 1, or is it just that that's the likely?
Yeah. So no, I didn't. So what you'll play this game. Suppose I choose n to be 0 and m to be 1. Can I do a match? Turns out no. What if I pick different values? So what you do is you try a bunch of things and see what works, what sticks. I'm not going through this and saying what doesn't work. I'm only saying what does work. I will do an example, probably 2 classes from now, where it's not clear what you should choose. And so we're just going to have to go through and check a couple. And finally, we land on something where you do get a match. In fact, we're going to have to take, it's going to be an example where we take n equals to, I think, 0 and m equals 1. So that's the only way we can get a match. Then I suppose the next match you could do would be n equals 2, or sorry, n equals 1 and m equals 2. So they're always off by 1. But this one, you can kind of tell what's going to work. Both solutions are written in terms of a power series in epsilon to integral powers. And so that tips you off that you're probably going to do a match, which is sort of balanced 1 for 1 and 2 for 2, etc. But well, I'll show you an example in section 3, 4, 5, something like that, where it's not clear what we can use for a match. And so we have to try a couple things and we'll see what works. And we eventually find out that you use a different value of n than you use for m. And that kind of makes the whole process cool. That's a great question. Thanks. Any other questions? So let's compare these guys. So I've chosen here epsilon equals 0.1. This is the true solution, which I showed you how to compute last time, or at least I exhibited the true solution for that ODE. And here's the 0, composite solution, this yellow, kind of orange yellow curve. I don't know what the actual color there is. Some of you probably can't see that color anyway, because it's too far away, or maybe you're colorblind. I called it yellow in the notes. Then we have this green solution curve or approximation curve. This is my 1-1 composite match, or my 1-1 composite uniformly valid approximation. So that one is basically overlying the blue curve, which is the true solution. You can't see the difference. So it's a very good approximation. Okay, so 1-1 match or 1-1 composite solution should do better than the 0-0. In fact, this is generally the case. In fact, what we want to show generically is that if I do y minus yc, let's say 0-0 to start with, I don't even have to write it like that, just can write it like this. And this is going to be order epsilon. So using just the leading order term, then the difference between that and the true solution in that leading order composite approximation, that's order epsilon. In other words, it's a first order approximation. Basically, you can view it like this. This is getting all the lower order leading order terms that are available here, and the only thing left over are order epsilon terms that you're leaving out. And if I do this match, or if I do this comparison, what do you suppose that O is? What's that big O of? Anyone want to guess? Yeah, it's just epsilon squared in this case. So you're basically capturing every term in the true solution with this uniform approximation of leading order and first order in epsilon. And so the only things you're leaving out are the order epsilon squared terms. And so this difference is order epsilon squared. So I would love to take a class and prove that rigorously, but I think if you guys see too many more rigorous proofs, you're going to gouge your eyes out. But I will put it in the notes, a proof that. So I discovered a couple of nice proofs for things like this. And so maybe not this semester, but eventually down the road, you pick up a copy of these notes, you'll see the proof of that fact in there. All right, let's talk about existence of solutions. Now, again, I don't do things in this course just to be mathematical. We're doing things so we can learn information. And this exercise in understanding when we have solutions to certain ODEs or boundary value problems is so that I know what to do when I go through my matched asymptotic approximation methods. So the first thing, let's fix what we're actually interested in here. Let's suppose that P and Q are continuous functions on this interval, x0 to x2. I could have worked with 0 to 1. I'm not sure why I didn't, but I chose some finite interval on which we're going to operate. P and Q are functions now, and they're functions that multiply these lower order terms, the first derivative of x and the 0th order term in x, or the first order derivative of u with respect to x, and then the original function u of x. P goes here, Q goes here. Now, we're only going to consider operators where epsilon is out front. Epsilon is a small positive parameter, okay? Small positive parameter. Now, for our initial analysis, we're just going to say it's positive. But the idea is, usually, and I probably should have said this, the easiest way to say it's small is just to say epsilon is smaller than 1, but greater than 0. So here's the differential operator that we're going to consider in this section. You can see that it's more general than the example that we just did. In the example we just did, this was a 2 and this was a 2. Okay, so it definitely generalizes that. And this differential operator acts on a u. So if you put in a different function u, then I'm going to get a different function in the end. I'm going to tell you how this function looks. So I should say L is an operator. And so when I put dot dot, that means the next thing that's going to follow is its domain. So the domain for this operator is are C2 functions. They don't have to be C2 all the way up to and including the boundary. Don't have to include the boundary, just a C2 function that goes up to the boundary. And what does it do? It turns that C2 function into what? A number? What does it turn it into? Yeah, a continuous function. And at best I can say is that it turns it into a continuous function, not a C1 function, not a C2 function, not a C infinity function, because every time I take a derivative, I remove regularity. When you integrate something, you make it smoother. When you take derivatives of a function, you get a rougher function. Okay, so you probably have all heard of this. If you haven't, then that's a freebie out there for you. So L is an operator. It so happens that it's what's called a differential operator. So I take one function and I create a new function from it by taking derivatives. And so this is exactly what I do. All right, so keep that operator in mind. I'm not going to keep showing it again and again. Take a Polaroid picture in your head. There's the operator that we're going to be using. All right, suppose my usual things. Consider the homogeneous boundary value problem consisting of the following equation. So this now is what we call a second order differential equation, right? It has an operator on one side set to 0. For all x between x equals x0 and x equals x sub 2. L is the differential operator on the previous page. And we want to use these homogeneous boundary conditions. So we say that this is what we call the homogeneous problem. It has homogeneous forcing term and homogeneous boundary conditions. What should be the solution to this problem? Does anybody want to guess? What should be the solution to this? Suppose it's a physical model. Okay, so this is a physical model where, think about it as a spring system. You put actually no load on the spring, and you don't stretch the spring at the end. What should the spring do? Nothing,
No.
right? So the solution should be 0. It should be the rest state. So we say the homogeneous problem has only the trivial solution if and only if u equals 0 is the only function that satisfies equation 18 and the boundary condition 19. We say that the homogeneous problem has a non-trivial solution if and only if there is a function that is not everywhere 0 that satisfies equation 18 and the boundary condition 19. So can we have a setup like that? Can we have an equation that has a non-trivial solution? Yeah. Okay. Just like you can have a matrix. So if I have a matrix that has that such that when I multiply the matrix times a vector, I get 0. Does that mean that this vector has to be 0, even if this matrix is a square matrix? The answer is no. There can be something non-trivial in the kernel for that matrix. So that would mean that this matrix is kind of bad in the sense that it's we call it a singular matrix, right? So
the differential operator is kind of like not like rank efficient.
it's like saying this problem, if I want to express it as an operator, as a big operator, okay? So we write that like this. Because the big L takes into consideration the differential operator plus the boundary conditions, okay? All right, if I set that equal to 0, then that's saying if there's something non-trivial that solves this problem, then we say that script L is not invertible. It's linear, but is not invertible. Okay?
Is that typo? Your U should be in C2, X not X2, intersect C of X not X2.
Yes. The typo is here. That should be X not X2. Closed brackets. So that's closed interval. Yes, usually, so the idea is you have to have this as your solution space because you need this much regularity so that the differential operator can act, and you need this much regularity so that the boundary conditions can make sense. Okay. Any questions about that? So can an ODE problem have a non-trivial solution? Yeah, but we really want to cook up something where this really only has the trivial solution, because then it's like saying that it's a non-singular operator. That's like saying that this guy has only the trivial solution What do we know about a matrix if this has only the trivial solution? Yeah, it's a full rank or invertible matrix. All right, so has anyone heard of this theorem before? You've probably seen or heard of variations of this, at least. This is called the Friedholm alternative theorem. It says this: suppose that our usual assumptions hold. Suppose that A and B are real numbers. Then the boundary value problem consisting of this operator set equal to 0. So notice that this part is homogeneous, where L is the differential operator in equation 17. So remember, put that mental snapshot in your brain. That's the differential operator we're thinking about. Second order, linear, non-constant coefficient differential operator. Okay, so this equation with the inhomogeneous boundary conditions, y of x naught equals A, y of x2 equals B, has a solution, a unique solution, in fact, if and only if the homogeneous problem consisting of equation 18 and boundary conditions 19 has only the trivial solution. That's the so-called Friedholm alternative. Now, that's a little bit like saying the following. It's entirely equivalent in the matrix world to this. Suppose that I know that this problem has only the trivial solution. That implies only the trivial solution. That implies that this always has a unique solution, no matter what right-hand side I put there, correct? If this has only the trivial solution, if and only if this has a unique solution for every B. We say that like this. There exists bang X Rn for every B in Rn. That's the math way of saying that. There exists a unique Xn in Rn for all Bn in Rn, or B in Rn, solving this if and only if this has only the trivial solution. Okay, it's exactly analogous to that. But the only thing I'm doing here is I'm inhomogenizing that. Yeah. No, this is inhomogenizing. Yeah, I'm reversing it. Inhomogenizing, dehomogenizing, maybe, the boundary conditions only. Okay.
It just follows from linearity, subtract the two solutions, and then you get the homogeneous boundary condition.
This one here, let's see. So
So
you're trying to apply what you know here to, right?
Yeah.
So let's see. That only has you. There's a little more to it than that. There's a little bit more to it than that. Just like there is for here, right? So if I know that this has a unique solution, then I can go this way. But it's harder to go this way, right? The same.
You by contradiction, you assume you have two.
Oh, okay.
solutions.
Well, yeah.
And
But how do you?
X1 minus X2 is your solution to the homogeneous system.
That's your uniqueness. But how do you prove existence? Yeah. Right. So there is a little bit more to it. Okay. But that's a good point. So I want to use this Friedholm alternative to give me some and what I know about this homogeneous solution to give me some indication about whether or not this general problem is solvable, okay, for any A and B. Whenever A and B are equal to 0, that's what we call the homogeneous problem. Otherwise, it's the inhomogeneous problem. Okay, so here's a little transformation. This actually has a name, this transformation. And I saw it recently in a book and I forgot to write it down. But it's not super important, except that sometimes when you have a name, it helps you remember something, or at least helps you find it when you need it. Here's another error, right? This is another typo. That should be X not X do. Okay, so suppose that P is a C1 function and Q is now C0 function. Now I'm elevating P a little bit because I need it to be differentiable. And let's define the following function, F. F is equal to Q minus P prime over 2 minus P squared over 4 epsilon. Okay, so the reason I wanted P to be differentiable is so that when I add it to these other functions, F becomes a continuous function. Now, if U in this function class, here's another, you can see I make liberal use of copy paste. If U in this function class is a solution to the homogeneous boundary value problem consisting of equation 18 and boundary conditions 19. So that's the homogeneous problem. Same operator equation, same ODE, but the homogeneous boundary conditions 19. Then the function W, which is in this same function class, defined by W is equal to U times exponential of this function. So notice that this is a function of X, and so this exponential is a function of X. And I'm multiplying it times U. So this one is the transformation I was talking about. This one has a name. Does anyone know it? It's okay if you don't. It's not on the quiz, not on the exam. It has some name, but forgotten it. What's that?
What's the name?
I don't know the name. That's the problem.
I thought you said you don't.
No, I read the name in a book,
And you forgot about it.
and it's one of the stack of books on asymptotic analysis that I have. But now, yeah, I can't. It's a little bit like I know the song, I know how to hum the tune, but I don't know the name of the song. Okay, then this problem satisfies this homogeneous boundary value problem, consisting of this equation and with these boundary conditions. So the only difference here is that this guy now, this equation, this new equation has no first derivative term. Okay, it only has highest order, lowest order. Now, the reason why this is nice is because this is what we call a variational equation. Anyone here ever take calculus of variations or know a little bit about it?
Yeah.
Little bit. So if you look at a variational, well, okay, so this one is a variational equation. That's all I'll say about it. That's all that's important. Conversely, if we know that W is a solution to the boundary value problem consisting of equation 25 and the homogeneous boundary conditions, not 25, but should be, this one should be 24 here. That should be 24. So consisting of equations, suppose now, so this one is the forward direction here. If we start by assuming U is a solution to the homogeneous boundary value problem, 18, 19. So we start with this, assume U solves that problem. Okay. Then we can show that W, which is defined like this, solves this problem. Now the question is the converse true? And the answer is yes. Conversely, if W is a solution to 24 and 25, then U, defined by the undoing of this. So U is going to be the undoing of this by simply taking this function and throwing it to the other side. So that's just going to be the same exponential, but with a minus sign, right? No problem there. So the undoing of that transformation. So that U has to satisfy equation 18 and 19, that homogeneous boundary condition or so homogeneous boundary value problem here?
I found it. It's called review screen transformation.
Okay. Did you use ChatGPT?
Or JWKB transformation, name after for
What was the other name in there?
JWKB,
This one's green.
review higher degree. I mean, that makes sense. It's always done.
Yeah, so you said something interesting. You said this is going to be related to the WKB approximation.
JW,
Yeah, so that's actually our next chapter. So we're going to use that transformation in that setting. Liouville green transformation. Okay, so that's the statement of the theorem. If you solve that one boundary value problem, then you solve the other one. And if you solve the other, then you solve the one. And the way you do this is just, start off by assuming that U solves that problem, introduce the transformation, introduce the W, and then you can show that then W satisfies this equation. Okay, it's not too bad. Now, clearly, W satisfies the boundary conditions, right? See that? Because this can never be equal to 0. Exponential of something can never be 0. So W at x0 has to be the same as U at x0. And same with x2. So we're good to go on boundary conditions, even in the undoing case. The question is, does W satisfy this? Well, all you have to do is multiply U times this guy and then check. It's a calculation check. All right, so simple should be in air quotes because it is a lot of derivatives and things like that, but it's at least the approach is simple. Questions? So why on earth did I transform my one homogeneous boundary value problem to another homogeneous boundary value problem? It's because I know how to analyze this one. Because this one is the one of variational type, it's amenable to variational tricks and tactics, whereas the other one is not because it's not a variational type. Has anyone ever heard of Sturm-Liouville theory? You can also turn the other one into Sturm-Liouville type, and then you can try to attack it because Sturm-Liouville type can be thought of as a variational type as well. Okay. Next theorem, okay? So again, I'm stating results here in theory, not because I like to prove theorems, which I do, and I like theory, but this is a course about applications, so this is going to help us understand something. So suppose the usual things, P now is elevated to be a C1 function, Q is just a C0 function, the homogeneous boundary value problem consisting of equation 18, and the differential equation 18 and the boundary conditions 19. So let me just flip back. So that's this guy. Okay. That's my problem that should only have the 0 solution if life is good. So suppose that this has only the trivial solution. Oh no, sorry, I said that wrong. This homogeneous boundary value problem has only the trivial solution if one of the following two sufficient conditions is satisfied. If I know one of these two things happens, then I know that 18 and 19 has only the trivial solution, and that tells me a cascade of other things as well. Here's the first condition. Suppose that P of X is not equal to 0 for X in x0 to x2. What does that mean? P is a continuous function. In fact, P is a C1 function that's never equal to 0. That means it's either positive or negative on the interval, right? Strictly positive or strictly negative on the interval. And suppose that epsilon is sufficiently small so that this guy here is greater than this guy here. All right, so let's look at this. So P is never 0. That's great. So this guy here is a positive number. Well, it's a positive number for every x. What happens if I divide it by epsilon? Epsilon is small. Think about that. So I can make this thing as large as I want. I can kind of blow it up. I can make epsilon small as I need so that this function, this positive function, eventually dominates this function. All right. I don't care what P is. As long as I know that P is either positive or negative on the whole interval, it doesn't have a 0, I can choose epsilon to be large enough so that this always happens. So that's condition 1. Really, condition 1 is just this. All right, so condition 2 is a simpler condition. It says that this function here is less than or equal to 0. Q minus P prime of x over 2. Now notice that this guy, that they're the same. And what about this guy? Well, notice that those were the constituents of f. In fact, there's the first part, and the second part was minus that. So what if I set f to be equal to 0? I could throw this guy to the other side, right? Basically, I get something which looks like that. Okay, so these are my two sufficient conditions. What's going on with these? Well, let's suppose that W is a solution to the boundary value problem consisting of equations. Again, I wrote that incorrectly. That should be 24 and 25. Okay. I think what happened was I copied the same label to both of these. So I'm going to have a copy error everywhere. That's okay. I can fix it. That should be 24 as well there. Suppose that W is a solution to the homogeneous boundary value problem consisting of equation 24 and the homogeneous boundary condition 25. Now, what we're going to do is multiply equation 24 by W, and we're going to integrate. So if I multiply equation 24 by 0, I get 0 equals integral from, and I'm integrating over the interval 0 to x0 to x2. So I have this integral to compute. Now remember that W has 0 boundary conditions, right? It's 0 at x equals x0 and x equals x2. I'm going to take this term here and I'm going to integrate by parts. It's the usual trick. So I'm going to integrate by parts, and when I do that, I get a minus epsilon integral from x0 to x2. So I get two terms that multiply each other. First derivative of W times the first derivative of W. That's another way of saying the first derivative of W squared. The boundary term goes away when I do that integration by parts. That's because W is equal to 0 on the boundary. The second term stays the same. W times, let's see, no, so W times FW. So this just gives me FW squared integral. All right, so we used integration by parts to treat that guy and use the boundary conditions. So here's what we have. Got this guy, set equal to 0. Now, either of the conditions above you can check lead to f being less than 0, less than or equal to 0. Condition 1 leads to f less than 0. Condition 2, so that's for you to check. So if either of the two conditions hold, you're going to check that they both imply this is true. That function f that we defined a couple of pages ago is less than or equal to 0. If this is the case, then we can argue that this guy has to be equal to 0. Why is that? Why is that? Well, what I'm going to do is I'm going to take this guy and throw it to the other side. So let's think about that. So we have integral x naught x2 f of t epsilon w squared t dt is equal to epsilon. So the difference is 0. I'm just going to write this very simply as w prime of t dt.
So left-hand side smaller than equals to right-hand side greater than equals to.
Right, so this guy, f is everywhere negative or less than or equal to 0, right? So we can argue then this has to be a negative number because its integrand is going to be non-positive. But this one, the integrand is non-negative, right? So this number has to be something, this number over here has to be something which is smaller than 0, smaller than equal. But what do we know about this one? It's got to be greater than or equal to 0, correct? Well, luckily we have a little bit of room so that this can still hold. The only possibility though is that everywhere it's 0, right? This is 0 and this is 0. So if f is less than or equal to 0, then the only possibility is that both of those integrals are 0. But if both of those integrals are 0, forgot to say 0, both of those integrals are 0, then I can argue the only way this can happen is if w is equal to 0. Why? Because w is a C2 function, right? So the only way that the derivative of w squared integrated can be equal to 0 whenever w is a C2 function is if w is everywhere equal to 0. That's it. So using a previous proposition, we can conclude that the homogeneous boundary value problem consisting of the differential equation 18 and 19 has only the trivial solution. Well, why can we do that? Well, remember that we said that U solves this problem if and only if W solves this problem. We just showed that W is equal to 0 everywhere. But remember that reverse transform, the reverse Liouville-Green transform given here, says that U has to be everywhere 0. Okay. And so that's great, but you could argue, well, that's just saying that 0 is a solution, right, to the other problem. But actually what this theorem says is a bit more. It says that the solution sets are mapped to each other. One solution or one system has one and only one solution if and only if the other has one and only one solution. It's a bit like saying those solutions are connected by a cord, all right? So this one, and they're intimately connected. So this guy over here has to be non-zero if and only if this one is non-zero, and vice versa. This one's 0 if and only if this one's 0. So if I know that W is 0, then that tells me automatically that the only solution to the other problem has to be 0. That's it. No other options. Okay, so that tells me that 18 and 19 can only have the trivial solution if what? If condition 1 or condition 2 holds. They could both hold, but both of them are sufficient conditions, so I only need one to hold. So if this holds, then f is less than or equal to 0. Now, can you see why that's true? All I have to do is move this guy to the other side, and that becomes f, and that says that f is less than 0. This one's a little bit more complicated. How do I see that one? Well, if I look at what f is, then I'm going to have something which is negative, and I'm going to add something which is also negative. So that's less than or equal to 0, and that's why that's true. You can check those two things, though. All right. Yeah, I guess I told you to already do that, but we mostly did it. So now, here's the punchline. If one of those two sufficient conditions from the theorem holds, from the previous theorem, then I know that my original boundary value problem has only the sorry, I'm getting ahead of myself. What we just proved is that if one of those two conditions hold, then the homogeneous problem has only the trivial solution. Now let's invoke the Friedholm alternative theorem. So that knowledge combined with Friedholm alternative says that the original problem, the inhomogeneous problem consisting of equation 20 and 21, has to have a unique solution. Okay, so that gives me a very simple test to check to see whether or not I have unique solutions or not. Remember, this whole course is about computations. So the question is that computable or not? Is this computable? Well, yeah, you know what Q is and you know what P is, so you can easily check this condition and this one. Actually, this condition is the only one you have to check because you could always make epsilon small enough so that this happens. You might not know exactly what epsilon to use, but you do know that for epsilon small enough, I can make this happen. And then you can check this one. It's not hard. You can calculate the derivative of P. You know what Q is. You can combine them together. And you can check to see, does that thing ever go above 0? If not, we're good. All right, so that's the corollary. Just apply the Friedholm alternative theorem, and that says that the two sufficient conditions from the previous theorem tells you whether or not you have a solution to your differential equation or not. So that's the differential equation we're going to solve. In fact, all the problems that we looked at so far are of that type. Okay. So the previous problem, we had P of X equals 2 everywhere. So the very last problem we did. So does that problem have a solution? Well, yeah, because we exhibited what the solution is. It's a constant coefficient problem, so it's kind of easy to check. So we knew that one had a solution already, but this just confirms that it does. Okay, the P function is positive, and so epsilon for sufficiently small epsilon becomes that becomes solvable. Actually, let's check that. So here, Q would also be 2, right? So this would be, if we're going to check it for Q equals 2, P equals 2, I probably ought to make one of these a P, right? P equals 2. So then this is going to be 2 minus, what's the derivative of P when it's 2 everywhere? It's 0. Is that less than 4 over 4 epsilon? Okay, so this cancels, right? So we have to have 2 less than 1 over epsilon. So as long as epsilon is smaller than a half, we're good, right? We're good. Any questions? Now, these are sufficient conditions. They're not necessary conditions. So actually, that previous problem has a solution for every epsilon. So it's just that the sufficient conditions don't tell us the necessity of things. Right? Yes.
Sorry, what's the difference between sufficient condition and necessary conditions?
Sure. So I say A is sufficient for B if the occurrence of A implies B. And we say that B is necessary for A because if not B happens, then not A is going to happen. Or in other words, if B doesn't happen, then there's no way in hell A is going to happen. Okay. So this means A is sufficient for B. Okay. A is sufficient for B. That's what we mean by A implies B. And we say that B, in this case, if this is true, then B is necessary for A. Because not B implies not A. Or maybe you've seen it like this. Maybe a more common notation is right? If I negate B, then negative B or negated B implies negated A. Okay. Okay. All right, next topic is how do we find the location of the boundary layer? We need this theory of existence to tell us when we have a solution, but it's also going to help guide us a little bit whenever we want to go to locate the boundary layer. So far, we've only ever said that the boundary layer is located at x equals 0, or the left-hand boundary, right? But we want to exhibit examples of all types where the boundary layer could be in the middle, it could be at the left-hand endpoint, but it could also be at the right-hand endpoint. So next class, we're going to talk about theory, which tells us where the heck the boundary layer could be expected to be located. And that helps us figure out, well, first of all, where's the location of the boundary, then it tells us what we need to do to select the boundary layer to thickness, and how we can choose or solve for our inner and outer problems. Because remember, we need to know where the boundary layer is in order to know what boundary conditions apply to the outer problem and what boundary conditions applies to the inner problem, and vice versa, right? Okay, see you guys on Tuesday. There will be a homework posted soon. Might be tonight, might be tomorrow, probably more likely tomorrow. Maybe even leaking into the next couple of days. And then once I give you that homework, then I'll tell you when it's due and all the rules and everything like that. Give me your homework grade in the next week or so. You can take, if you need to take a little extra time to correct some problems, then take that time, whatever you need, and then send me your grade once you have it. You can see you can refine the process until you get exactly the grade you want. So you can stop whenever you're happy. Have a nice weekend, guys. See you on Tuesday.